Hello. Again, we are here to talk something about metric space, and in this video we are going to talk about distance between point and set, distance between two sets, and diameter of a set. In this video we are going to talk about the definition as well as we are going to take some examples and some problems to explain these concepts. Before I proceed to have the concept of these points, I once again remind you to please subscribe to my channel and hit the notification bell so that you get the notification as and when the videos are loaded on the channel. So let us proceed and now have the definitions of various topics which we are going to deal with in this video. The first topic which we are going to discuss is the distance between point and set. Here the definition is in text on your screen, but we are going to explain it a bit with the help of the picture shown on the screen. ED is taken as a rectangle on your screen. I don't say that any metric space can be represented by a rectangle, but just to explain the concept and for the lucidity in the explanation, I have taken the rectangle as a metric space. The set A is taken as a circle and X is any point in the metric space. Now we have to see the distance between point and the set in the sense of the metric which we have defined on the metric space. But for simplicity, what we are doing here, that we are drawing lines from X to points of the set A. So in fact, we have to find all the distances from the point X to all the points present in the set A. We may denote these points by alpha, and you can now see very easily that there could be infinite number of such distances from the point X to the points present in the set A. But as far as the distance from X to the set A is concerned, we are going to consider the least possible distance from the point X to the set A, which I am going to show you with the red line. I once again repeat that it is not essential that the distance from a point to another point is represented by a straight line. In fact, it depends on the metric which you have defined on the metric space. Now, after observing this picture, let us have the definition of this notion of distance between point and set. This is very simple. What we are doing, that we are measuring distance from X to the points alpha of the set A. So let us write dx alpha. This is the distance between the point X and the points alpha of the set A. Now alpha varies over the set A. So I am writing alpha belongs to A, and we have to consider all the distances. So I am taking a set of all the distances. Be careful that the point X is a fixed point of the set E, and in fact the metric space E, and alpha is a point which is varying on the set A. Now we are seeing the distance of X from the set A, or the distance of the set from the point X, as the least possible distance, and you know that if this set dx alpha contains the least element, then that is going to be the distance from X to A. Otherwise, since you can have infinite number of members in this set, we can see infimum as the least of all the distances, and this infimum is going to be dxa. Now it is very clear that if A is non-empty, it simply implies that dxa is always going to be greater than or equal to 0. But think about the empty set. Now if the set is empty, then this set is going to be empty, and therefore what happens, you are taking the infimum of an empty set, and you know that infimum of an empty set is plus infinity, and therefore I can write that dxa is equal to plus infinity, and it is true both ways. So we can write A is equal to phi. It implies and is implied by that dxa is equal to plus infinity. Now we are moving to have a problem or a remark rather on the concept of distance between point and set. Let us move and see what is that remark. Now the remark is on your screen, and we are simply saying that if X belongs to the set A, then dxa is always equal to 0. But dxa equal to 0 does not anyway imply that X belongs to set A. And we are giving an explanation to this remark. See, this set dx alpha belonging to A, this set contains only non-negative real numbers, because you know dx alpha is always greater than equal to 0 due to the first property of a metric. Further, since we have to take X belongs to A, if X belongs to A, then dxx will be a member of this set, because this alpha has to vary on all the elements of the set A. So dxx is a member of this set, but dxx you know is equal to 0. So 0 becomes a member of this set, and therefore if 0 becomes a member of the set, which is in itself a set of non-negative real numbers, it simply gives you that the infimum is going to be equal to 0, and this infimum is nothing but dxa, and therefore we simply see that dxa becomes equal to 0. So if we take X belongs to A, then we find that dxa is equal to 0. Let us see the converse. For converse, we are taking RD with usual metric. So usual metric means if I take dxy, then this is modulus of x minus y. This is the usual metric on R. Now what we are doing, we are taking a point x equal to 0 and a set A with semi-open interval 0, 1, and therefore we note that x is not a member of A, because x is 0 and A does not contain 0. Now let us see what is dxa. By definition, dxa is infimum of dx alpha, where alpha belongs to A. But how can you write this dx alpha? You know the metric is dxy is equal to modulus of x minus y. So dx alpha can be written as modulus of x minus alpha. But x is 0, so this is modulus of 0 minus alpha, where alpha is any element of A. Now let us see what is A. A is the set starting from the 0 to the number 1. It is an interval, you know, semi-open interval, and therefore any member of this set A is of the type epsilon, where 0 is less than epsilon and epsilon is less than equal to 1. And therefore we can write modulus of 0 minus epsilon, where epsilon has this range. Now it means that you have to find the infimum of epsilon, where epsilon is having this range, and you can very simply see that this infimum is equal to 0. If you don't know about infimum and supremum, you may see our video on this channel about infimum and supremum, or least upper bound and greatest lower bound. Now let us move and see another concept, which is distance between two sets. Now on your screen again there is a definition of distance between two sets, but let us explain it very clearly, that distance between two sets A and B, in fact you have to find distances between all the points of these sets. So you have to find the distances from each point of B to each point of A. And the distance between B and A is nothing but the shortest possible distance between a point of B and another point of A. Now how to write it mathematically? This is very simple. What we have to do, that take points from A and B. I am taking alpha from A and beta from B, and I am writing alpha belongs to A and beta belongs to B, and we have to take all such distances, and then we have to think of the shortest possible distance. You know, if a set having infinite number of elements, then if it is having the least element as a member of itself, then the least element is going to be the infimum. Otherwise, you have to find infimum in another way, and that infimum is going to be DAB. We can think of the minimum if the set is finite, but if a set is having infinite number of elements, then we cannot talk of minimum, we can talk of infimum only. And therefore, we have to find DAB like this. Now, for DAB, we can have also a remark. What is that remark? Let us see. Now, on your screen, there is a remark that if A intersection B is non-empty, then DAB is equal to 0. This is very important. A intersection B is non-empty, then DAB is equal to 0. But we can have DAB equal to 0 even when A intersection B is equal to empty. So if you are having DAB equal to 0, you please don't jump to conclude that A intersection B is non-empty. It can be empty as well. Now given that A intersection B is non-empty, we are taking X in A intersection B. And then we set this D alpha beta alpha in A, beta in B contains dxx equal to 0 because X then belongs to A as well as X belongs to B. But dxx is equal to 0 and therefore this set D alpha beta, alpha in A, beta in B contains non-negative reals with 0. And hence the infimum of this set is going to be equal to 0 and that infimum is nothing but DAB. So if you take one element in A intersection B, it means the distance between the set A and the set B is always going to be equal to 0. Conversely, if we take RD with usual metric, again a usual metric means the metric with the modulus sign. We are taking two sets A with interval 0, 1 open interval, B also open interval 1, 2, and then we see that A intersection B is empty. But now we will see that DAB becomes equal to 0. How? We are taking epsilon, any arbitrary positive number, and we are setting alpha is equal to 1 minus epsilon by 3 so that it becomes smaller than 1 and it becomes a member of the set A. We are also taking beta as 1 plus epsilon by 3 so that it becomes greater than 1 and becomes a member of the set B. Now if we calculate D alpha beta, then according to the definition of the metric, it is going to be modulus of bracketed 1 minus epsilon by 3 minus bracketed 1 plus epsilon by 3, which is 2 epsilon by 3. Now it simply gives that D alpha beta, which is being a metric, is always non-negative and therefore it is 0 greater than equal to D alpha beta, and this is going to be less than epsilon because it is equal to 2 epsilon by 3. Now this gives you that D alpha beta is equal to 0. But once D alpha beta becomes equal to 0, since it is a member of this set, the infimum of this set is going to be equal to 0 and this infimum is DAB, therefore DAB becomes equal to 0. So here you see that A intersection B is equal to phi, but even then DAB becomes equal to 0. Now let us move and have the concept of diameter of a set. Now on your screen there is a definition of diameter of a set, but here again a metric space is shown by a rectangle and a set A in a circle. Now what we have to do, that we have to measure all the distances between 2 points of the set A. So you can have all the possible distances. Again I am repeating that I am showing all the distances with the help of a straight line, but you know that distance has to be measured essentially as the definition of the metric D. So we are just putting it as a straight lines just to understand the concept. Now what is the diameter? Diameter is going to be the largest possible distance between 2 points of the set A. How can we define mathematically then? This is very simple. What we have to do, you have to take the distances between 2 points of A. So alpha 1, alpha 2 are 2 points which belong to A. So alpha 1, alpha 2 belongs to A. Take the set of all such distances. Now you have to take the greatest possible distance. Again I am repeating that this set can have infinite number of points. So the greatest member, the supremum, and this supremum is nothing but it is called as the diameter of the set A. It is denoted by delta. It is a custom to denote it by delta. There are also other notations, but you can adopt delta as it is in vogue. After talking about the distance, we are going to see some problems. These problems will explain you the concepts in a much clear way. Let us see those problems. Now here we are giving that dxy is modulus of x minus y on R. There are sets A and B and we have to find these quantities. Let us see what is the solution. First we are going to see delta A. So what is delta A? For delta A, what we are doing, that let us see on the straight line that this is our set A. Now on the set A, you can see that 2 doesn't lie on that straight line. But what will be the end point? The end point will be something like 2 minus epsilon. What will be the range of epsilon? Certainly epsilon is positive because it is smaller than 2. So 0 is less than epsilon. But you can see that if you slide this line, then it will assume the value 1. And therefore the value of epsilon can be less than or equal to 1. So that when epsilon assumes the value 1, 2 minus epsilon assumes the value 1 as well. You can see delta A, because you know the definition of delta A gives you that it is the supremum of all the distances between any 2 points of the set A. But we know that A is an interval, and therefore largest possible distance between 2 points of the set A is always going to be the distance between the end points. So what we are going without loss of generality, that we are writing delta A is equal to supremum of modulus 2 minus epsilon minus 1 such that 0 is less than epsilon less than equal to 1, and this is supremum of 1 minus epsilon, where epsilon ranges like this, and then if you get supremum, it is going to be equal to 1. Now we have to calculate delta B. So what is delta B? If you calculate like this, delta B is going to be equal to 2. Now DAB. For DAB, what we do, that we refer to an example which we have already discussed. Now this is the example which we have seen, and we have found that DAB is equal to 0. Exactly in the same fashion, if you do calculation, then here again you will get that DAB is equal to 0. Now the next is D of 1.5b. Let us sketch the set B. Now this is the set B, you can say, and in the set B you can see that any element is of the type 2 plus epsilon, where epsilon is certainly not 0 because 2 is not present in this set, and it will go up to 2. Now 1.5 could be somewhere here, and therefore because D is an interval, again we can see it as the difference between 2 plus epsilon and 1.5, where certainly epsilon has that range between 0 and 2. Now this is equal to infimum 0.5 plus epsilon, where epsilon is like this. If you have to find epsilon, if you have to find infimum, then epsilon has to take the smallest possible value, and in that case the infimum is going to be 0.5. Now next we are going to discuss is D 5 by 4a. Now D 5 by 4a, you can very easily conclude that it is equal to 0. Why? Because 5 by 4 is a member of A. 5 by 4 could be somewhere here in the set A. So 5 by 4 is a member of A, and we have seen already that if X belongs to A, then dxa is equal to 0. Likewise, D9 by 4b is also equal to 0. Again, if you find D5b, then you can very easily see that this is equal to 1. So these examples must have cleared some idea in your mind. Now we are going to see another problem. Here in this problem, we have ED as a metric space, X, Y are members of the set E, and A is a non-empty subset of E. Then we have to prove this. This is very simple. We are taking Z in A as arbitrary element, then we can have triangular unity like this because of the metric space properties. Now dxa by definition is equal to this, but dxz now, because of this triangular inequality, now be replaced by this, and when we replace dxz by the right part, then you have to put an inequality here. Now this dxy, you can very easily see that x and y, these are both members of E, and therefore dxy is a fixed number. Infimum doesn't run on dxy now. So we can take dxy out of that bracket, and dxy plus infimum of this set, which is dxy plus dya. We can take dya to the left side and we can get this inequality. Similarly, you can get this inequality if you take y in place of x. Because of 1 and 2, you can very easily conclude that we are having this inequality, because simply you know that x less than equal to a and minus x less than equal to a. This implies that modulus of x is less than equal to a. So this way you can have the solution of this problem. Let us see another problem now. Now in this problem we are again having a metric space ED and AB are subsets of E. We have to prove this inequality, and if A intersection B is non-empty, then you have to show that the inequality will take this shape. Now we can take xy in A union B because we have to discuss the delta A union B. We can have 4 type of cases. First, that xy is entirely in A. Now xy in A gives you that dxy is less than equal to delta A, but because dxy is a distance between x and y, where delta A is the supremum of all such distances. And similarly, in case 2, if xy belongs to B, you can conclude that dxy is less than equal to delta B. In case 3, if we take x in A and y in B, then for any alpha in A and beta in B, we can have dxy less than equal to dx alpha plus d alpha beta plus d beta y by applying twice the triangle inequality. Now in dx alpha, x is a member of A, alpha is a member of A. So if we replace dxa by delta A, there is no problem because delta A is the supremum of all such distances. Now d alpha beta is remaining as it is. Now d beta y again can be replaced by delta B, because a beta and y both are members of B, and delta B is the supremum of all such distances. Similarly, in case 4, if you take x in B and y in A, then you can find that dxy is less than equal to delta B plus d alpha beta plus delta A. Here we are applying the symmetry part as well, because d beta alpha is being replaced by d alpha beta. But observe that in all the cases, you can find this inequality that dxy is less than equal to delta A plus delta B plus d alpha beta. This is true for all the cases, and therefore if this inequality is true for all the cases, we see that alpha in A, beta in B are arbitrary choices. It means it is valid for any alpha beta. We can replace d alpha beta by dab. So dxy is less than equal to delta A plus delta B plus dab. And therefore the right hand side becomes an upper bound for dxy. So we take least upper bound. This is also less than equal to the right hand side, and then we get that delta A union B, because this supremum is nothing but delta union B. So delta A union B is less than equal to delta A plus delta B plus dab. Lastly, you see that A intersection B non-empty always gives you that dab is equal to 0, that we have already seen in a remark, and therefore if dab equal to 0, then delta A union B becomes less than equal to delta A plus delta B. This way we have finished this problem. We are also coming to an end of this video, and I hope that these videos are going to be a bit helpful in your studies. So please do subscribe our channel and hit the notification bell. If you like the video, share the videos with your friends. In the next video, we will again meet with you. Till then, thank you. Bye bye.